Welcome back to another video. Today we're going to take a look at the grade 11, paper 1 for 2025. Question 1.1. Two forces P and Q act at a point O. As the angle theta between P and Q varies, the maximum and minimum resultant forces are 13 and 3 respectively. The magnitude of the two forces are. So this question is quite a straightforward question if you know what to look for. When we're looking for maximum of two forces, what we're really looking for is that the sum of those two forces will give us 13. So we're looking for two numbers such that when we add them, we're going to get 13. And when we're looking for minimum, we are then looking for the difference. So the difference of those two numbers will be 3 and the sum will be 13. So that's obviously then going to be C, because 8 plus 5 is 13 and 8 minus 5 is 3. Moving on to question 1.2. A passenger standing in a moving bus moves forward when the bus suddenly stops. This can be best explained by, and this is just us knowing the definition, and this is Newton's first law. Newton's first law basically says that when an object is stationary or moving at constant velocity, it's going to want to remain in that state unless acted upon by a net force. Question 1.3. A learner sits on a chair. What is the reaction force of her sitting on the chair? The action force, they tell us, is the learner or her on the chair. So action will be learner on chair. That means the reaction, and all we got to do here is switch the words. It's going to be chair on learner. So we're looking here for option C. Question 1.4. Force F acting at an angle of 60 degrees to the horizontal is applied to two identical blocks, A and B, lying on a smooth horizontal surface. The blocks, each having mass m, are in contact. The question says, what is the magnitude of the force that block A exerts on block B in terms of F? The first thing I'm going to do is I'm going to draw the free body diagrams for A and for B. So for A, I'm going to have the horizontal components of this force, which is going to be Fx. And we know that Fx is F cos theta, so that's going to be F cos 60, which is half F. Now the other forces that are acting on it are obviously going to be the normal force. There's going to be weight, there's no friction. However, because it is in contact with block B is going to be pushing block A to the left. So there's going to be a force of B on A here. Now, if I draw a free body diagram for block B, I'm going to have a normal force, so Fn, there's going to be weight, and there's going to be the force that A exerts on B. Now, I can apply Newton's second law to both of them. Here, I'll say that F net is equal to ma. Now, if I'm choosing right as positive, I'm going to say half F minus the force of B on A is equal to ma. Now, I'll do the same thing for block B. F net is equal to ma. The force of A on B is equal to ma. Now, we know that because these are action-reaction forces, the force that B exerts on A is going to be equal to the force that A exerts on B, just in the opposite direction. So I can write that the force of A on B is equal to minus the force of B on A. So implying that they are equal in magnitude but not in direction. So I can just replace this whole side here with FA on B, which is MA. So I can say half F minus, and this is MA, and that's equal to MA. So then half F is equal to 2MA, and that means that if I divide both sides by 2, I'll get a quarter F is equal to MA. So the answer here is going to be B. Now, the other way that we can solve the same question is if we think of the system as one entire system. So if I think of it as an entire system, I'm going to have both the masses combined, and they have a mass of 2m, and the force here is going to be half F. Now I can apply F net equals MA to this whole system. So I'll say that F net equals MA, then half F is equal to 2 MA. Now I can solve for A here. So A is going to equal 1 over 4M multiplied by F. Now I can say that the force of A on B is equal to MA. And remember, that's from here. But we know that the acceleration from here is going to be a quarter m times F. So the masses will cancel here. That means that the force of A on B is equal to a quarter F. Now let's move on to question 1.5. A car moving to the right along a rough horizontal surface is brought to rest by a constant net force. If the motion of the car to the right is taken as positive, which one of the following acceleration versus time graphs is correct for the motion of the car? If it's a constant net force, so we know that F net is equal to MA. If I have a constant F net and M is constant, then I know that F net is going to be directly proportional to A. So if this is constant, then this should also be constant. So we're looking for a graph where the acceleration is not changing. So that is out and that is out. Now, if the car is slowing down, that means acceleration is going to be in the opposite direction of motion. So if this is taken as positive, that means acceleration must be negative, otherwise the object is going to speed up instead of slow down. So the only option then is going to be D. Question 1.6. The graphs P, Q, R, and S are drawn below, showing a relationship between the force of attraction that two masses exert on each other and the inverse of the square of the distance between their centers. Which graph will the product of their masses be the same? F is equal to G m1 m2 over r squared. If I cross multiply here, I get FR squared is equal to G m1 m2. This is the product. If we take the gradient of this graph, F divided by 1 over r squared, that's going to be F multiplied by r squared over 1, which is FR squared. So essentially, the steepest gradient is going to be the one that's going to have the highest, the greatest product of the masses. So the answer here is going to be P, which is A. Question 1.7. The force of attraction between two charges Q1 and Q2 is F. If the distance between the charges is made 4 times smaller, then the new force of attraction will be what? We'll say that F is equal to K Q1 Q2 over, and what they've done is they've made the distance 4 times smaller. So essentially a quarter r all squared. Now we simplify, we're going to get K Q1 Q2 over 1 over 16 r squared. So 1 divided by 1 over 16 is essentially 16. And then K Q1 Q2 over r squared is F. So it's going to be 16 times the original force. So I should say that this is the new force. So the answer here is going to be D. Moving on to question 1.8, the north pole of a bar magnet is pushed into a solenoid as shown in the sketch. When a bar magnet approaches a solenoid, the solenoid will want to push the bar magnet away by inducing the same pole. So X will be north because it's going to want to push this away. So if that's the north, you can use your right hand grip rule. So imagine you are holding the solenoid, you're holding this cylindrical object. Your fingers from your right hand are going to be pointing upward here. So that means that the current is going to be moving from A to B. So the answer we're going to choose here, polarity of X is going to be north and direction of current is A to B. The answer is C. Question 1.9, the ampere second is a unit of what? Ampere second, so to answer this question, we look at what is A. So A is a measure of current, so I. And S is a measure of time, so that's T. So what is equal to I times T? So you look at your data sheet, you'll find that Q is equal to I times T, so that's quantity of charge. And the last question of the multiple choice, which one of the following graphs represent the relationship between the total electrical energy transferred, W, and the electric current in the element of a kettle? The resistance of the element and the time is the same. We can use a formula here, W equals I squared RT. So they tell us that the resistance is the same and the time is the same. So we can reimagine this as a constant K. So W is equal to K. Now, if we had I on our x-axis, this would be essentially y equals kx. Now that's a linear expression or linear equation, and it would look like this. So if I had w on my y-axis and I squared on my x-axis, then that would be linear. But if we have w on the y-axis and I on the x-axis, then it's going to look like a parabola. So the answer here, if you're looking at these graphs, since we have I on our x-axis, it's going to be C. That's going to be our answer. Okay, let's take a look at question number 2. Three forces, FA, FB, and FC act on a point O in the direction shown in the diagram. The magnitudes of FA and FC are 44 and 31 respectively. FB is unknown. Question 2.1, define the term resultant vector. It's important that you learn the correct definitions because definitions are usually 2 or 0. So if you miss something or you try to rewrite something, you're going to get 0. The next part of the question says the resultant of the three forces is 26,69 newtons at an angle of 25,82 to the horizontal and lies in the first quadrant. So if I have a Cartesian plane like this, then my resultant is going to be here. It's going to have a length of 26,69 and the angle is 25,82 degrees. I can then break this and make it into a triangle. That's going to give me two components now. So this is going to be the resultant component in the x direction. That's going to be to the right. And we are also going to have the resultant component in y direction. Now because this is a right angle triangle, I know the hypotenuse and I know the angle. I can use trig to work out the x and y component. So I can use cos to work out the x component. I can say cos of 25,82 is equal to adjacent, so FR x component divided by hypotenuse 26,69. That means if I cross multiply, FR in the x component will equal 26,69 times cos of 25,82, which is equal to 24,03 newtons. I can do the same thing for the y. So FR in the y component, and that's equal to, this time it's going to be sine. So it's going to be 26,69 multiplied by sine of 25,82. And that's going to equal 11,62 newtons. Now that I know the components of the resultant, I can then equate that to the components of FA, FB, and FC if applicable. Now FA, if I complete this triangle, is going to have a horizontal component that I'm going to call FAX. That's going to act to the right. And it's going to have a vertical component that's going upward. I'm going to call that FAY. Then similarly for B, it's going to have a horizontal component and a vertical component. I will call the horizontal FBX and the vertical FBY. Now because FBY and FAY are both acting upward and FC is acting downward, I'm going to subtract FC from the sum of FAY and FBY. I can say here that the vertical, now I'm looking at the vertical forces, it's going to be FBY plus FAY minus FC, and that's going to equal the vertical component, so FRY. Now let's substitute. So FBY is going to be, since this is opposite the angle here, and that's the hypotenuse, I can use sine. So it's going to be FBY plus FAY. I can use sine again to work out FAY. FAY is going to be 44 multiplied by sine of 28. Then minus FC, so minus 31, is equal to 11,62. FBY component equaling 21,96 newtons. So we can substitute here 21,96. Now we repeat the process for the horizontal components. Now C will not have any horizontal components, or FC rather, because it's acting straight down. So FAX minus FBX, because they act in opposite directions, is going to equal 24,03. Now I'm saying FAX minus FBX because the resultant is to the right. And since FAX is to the right, I'm keeping right as my positive direction. So I'm going to simply say FAX minus FBX is going to equal FRX. Now FAX is adjacent to the 28, so I'm going to use cos here. I will say 44 times cos of 28 degrees minus FBX is equal to 24,03. I can then solve. FBX is going to equal 14,82 newtons. So I can put here 14,82. Now I have a triangle, and if I want FB, that's the hypotenuse. So FB squared is going to equal 14,82 squared plus 21,96 squared. That means FB is going to equal 26,50 newtons. The last question, 2.3, determine theta. So theta is the angle in that triangle. We can use any trig ratio to solve for theta. I'm going to use tan here. So question 2.3, I can say tan theta is equal to opposite. So 21,96 divided by adjacent, which is 14,82. That means theta is going to equal shift tan or arc tan, and that's going to equal 55,90 degrees. Let's take a look at question 3. An object of mass m is attached to string Z and hangs vertically downward at point O. Strings P and Q connect point O to a horizontal ceiling, making angles of 30 degrees and 60 degrees with the horizontal respectively at point O, as shown in the diagram. All the strings are light and inextensible. Question 3.1, state what is meant by forces in equilibrium. So important for us to know here that the definition of forces in equilibrium means that the net force acting on the object is 0. So important here, there are some underlined words that you need to ensure that you have. If you don't, you will lose 1 mark for each underlined word. Question 3.2, draw a labeled closed vector diagram, so meaning a triangle, showing all the forces acting on point O indicate 2 angles in the diagram. So the forces are going to come from the following lines. So this line, and this line. So if we are drawing the forces acting on this point, P is a rope, and that there's going to be tension in that rope, and tension points away from the object. So it's going to go this way. Similarly for Q, it's going to go that way, and for Z, it's going to go down. Using those 3, we need to draw a triangle. So I can easily just draw Z going straight down. Then I can take Q and draw a diagonal going this way. And then from here, draw the last diagonal, which is going to be P. And that's going to be my closed triangle. Now they asked us to include 2 angles in the diagram. So if I look at Q is making an angle of 60 degrees to an imaginary horizontal line. So if I had to complete this, if I have to say that, okay, this is going to be 60 degrees. In that triangle, what angle is it going to make here? Now it's not drawn to scale, so it may not accurately represent what it actually is, but we can see that there is a 90 degree here. So 60 plus what will give me 90. The angle here is going to be 30. Now similarly, we can do the same thing for P. P is making an angle of 30 degrees to the horizontal. So if I draw a horizontal line here, this is going to be 30 degrees. So that means the angle inside must be 60. Now the last angle in this triangle has got to be 90, because some angles in the triangle must be 180. So if 60 and 30 make up 90, then the last angle must be 90. And that's going to be our closed vector diagram. Now question 3.3.1. They tell us the tension in string P is 50 newtons. So this here is 50 newtons. Calculate the tension in string Q. So it may be difficult to see like this. So let's redraw this triangle. So I've got a perpendicular, well, two perpendiculars like this. There's my 90, that's 90 there. This is going to be P, and that's going to be Q. This we've been given as 50. This we don't know. And this has got to be Z. Now Q and Z join at 30 degrees, and Z and P join at 60. Now it's a bit easier to figure out what trig ratio to use. So if we want Q, P is given to us, and we've got this angle 60, or we've got the angle 30 that we can use. So I'm going to use the 30 here. So I'm going to say that tan of 30 degrees is going to equal, now tan is opposite over adjacent, so opposite the 30 is P, so P divided by adjacent to the 30 is Q. Now if I want to solve, I can simply switch. I'll say Q is equal to P, which is 50, divided by tan of 30. That means Q is going to equal 86,60 newtons. So this is 86,60 newtons. Then 3.3.2. Calculate the mass of the object. So in order to calculate the mass of the object, we need to look at what rope is attached to the mass. It's Z. So we need to figure out what Z is. And if we can figure out what Z is, we can calculate the mass. So I've got these two. I can use Pythagoras to solve for Z. So Z is going to equal the square root. Now since it's the hypotenuse, it's going to be the sum of these two other two sides squared. So 50 squared plus 86,60 squared. That means Z is going to equal 100 newtons. Now that is the force of gravity. So Fg. Now Fg is equal to Z. Now force of gravity can be calculated as mass times gravity equals 100. That means the mass is equal to 100 divided by 9,8. And the mass therefore equal to 10,20 kilograms. Now the last question, question 3.4. In which of the strings P, Q, or Z will the tension be the greatest? Give a reason for the answer. Well, we've already worked out the values, and the greatest one is Z. P was 50, Q was 86.60, and Z was 100. So Z is the answer. Now they asked us to give a reason. And the reason is either because, well, you could say one of two things. You could say it's the hypotenuse. And the hypotenuse in a right angle triangle is always going to be the longest side. And so it's, in this case, it's going to be the greatest force. Or you could say that it's opposite the largest angle. So Z is opposite the 90 degrees. And because of that, it's going to be the greatest force or the longest side, or it's going to have the greatest tension. Now let's take a look at question 4. Learners set up an experiment to determine the coefficient of static friction for a block placed on an inclined plane. They set up the experiment as shown below. So they've got an adjustable inclined board with a block on it. They've obviously raised this board up to some angle theta, and they followed the following procedure. So they placed the block on the inclined surface, and the incline was adjusted until the block just begins to move on its own. That was run 1. The angle at which the block starts to move, so theta s, was recorded, and the procedure was repeated for an additional 3 runs. The data obtained from the above experiment is shown in the table below. So we've got the run, we've got the angle, and we've got the coefficient. There's also some values that were not given to us, so x and y. I'm assuming they're going to ask us to solve that at some point. Question 4.1 says define static friction in words. The definition, so we leave that out for now. Question 4.2, using relevant formulae, show that mu s is equal to tan theta. So let's draw a free body diagram looking at the forces acting on the block as it's on this incline. Now this is not part of the answer, so we can draw the components. So the forces acting here are going to be, this is going to be friction, so static friction max, because it's just about to move. There's also the weight parallel, so gravity parallel that's acting down the slope. There's also W perpendicular. And lastly, there's the normal force. Now remember, this is just about to move. So W parallel is equal to Fs max. And it's just about to move. Now W parallel can be rewritten as mg sine theta. And Fs max is mu s times Fn. Now we'll continue here. We've got mg sine theta is equal to mu s, and the normal force is equal to W perpendicular. And W perpendicular is mg cos theta. Now I can divide both sides by mg, so mg will disappear. And then I can divide both sides by cos theta. So I'll divide this side by cos theta, and I'll divide this side by cos theta. Then the cos theta will disappear, leaving me with tan theta equals mu s. And we've proven it. Moving on to question 4.3. Determine the values of x and y on the table. If we know that the coefficient mu s is equal to tan theta, then all we need to do is substitute 32 to get what x is. So we'll say tan of 32 degrees. And that's equal to 0.625. And then the last one, to calculate y. Y is the average coefficient. So you add up all of these values. So all of these. And then you divide it by 4 because there's 4 runs. And that's going to give you 0.65. Now question 4.4 says, angle theta is now set so that the block is allowed to slide down the incline at constant velocity. So how does the coefficient of kinetic friction compare to the coefficient of static friction? choose from greater than, less than, or equal to. Now this is more of a theory question, because all you need to do is just remember that kinetic friction is always going to be less than static friction. Well, Fs max. Because the graph looks like this. So static friction can go from 0 all the way up to Fs max. And then after Fs max, the block begins to move. And it then moves with kinetic friction, which is lower and a constant value. So the answer here is less than. We can go a bit more in detail here because the question is asking for the coefficient. So Fk is equal to mu k times Fn. And Fs max is equal to mu s times Fn. Now, because Fn is common to both, we can take away Fn. That means Fk is going to be proportional to mu k, and Fs max is going to be proportional to mu s. So if Fk is less than Fs max, it means that mu k will be less than mu s. Moving on now to, well, this was question 4.4. Moving on to question 5. A man of mass 80 kilograms stands on a scale placed on the floor of a stationary lift. The mass of the lift is 1,500 kilograms. When the lift accelerates upward, the tension in the cable T is 17,000 newtons. State Newton's second law. We can come back to that at some point, but it's a definition, so it's just about learning it. 5.1.2, calculate the magnitude of the acceleration of the lift as it moves upward. So we can apply Newton's second law. We'll say F net equals ma. Now, the forces that are acting on the lift are going to be tension. So tension is going upward, and there's the force of gravity going downward. Now, since it's moving upward, it makes sense to choose up as positive. So we'll say that tension minus Fg is equal to ma. Now, we are asked about the acceleration of the lift, so we need to take the whole thing into account. So the whole system. So the tension is given as 17,000 minus Fg is mass times gravity. So the mass of the lift is 1,500, and there's a man inside with a mass of 80 kilograms. So that's 1,580 multiplied by acceleration due to gravity, which is 9,8, and that's equal to the mass of the lift, 1,580, multiplied by the acceleration of the lift. We can then solve for A. A is equal to 0,96 m dot s to the power minus 2, and direction is upward. Moving on, question 5.1.3. Will the reading on the scale be greater than, less than, or equal to the weight of the man? Briefly explained by referring to the forces involved. So we can focus on the man now. If I look at the forces acting on the man, there's going to be the force of gravity, and there's going to be the normal force, so Fn. The normal is the reading on the scale. Reading on the scale. So we can apply F net equals ma for this man. So F net equals ma. Now the man is moving upward, so it makes sense to choose up as positive. So we'll say Fn minus Fg is equal to ma. Now Fn is the reading on the scale. So Fn, which is the reading on the scale, is going to equal ma plus Fg. That means that the reading on the scale is going to equal the mass times the acceleration plus the weight of the man. So therefore, the reading on the scale will be greater than the weight. Because it's clear here that we are adding on MA. Moving on to the next part, the lift now accelerates downward at 1 meter per second. Calculate the reading on the scale. So 5.1.4. Now the forces are still going to be the same, but now we have acceleration that's going downward. Since acceleration is going downward, it makes sense to choose down as positive. So we'll simply say F net is equal to MA. This time I'm going to have FG minus Fn is equal to MA. Now Fg minus MA will equal Fn. And keep in mind that Fn is the reading on the scale. Reading on the scale. Now, the force of gravity is going to be the mass of the man. So the mass of the man is 80. Acceleration due to gravity is 9,8 minus the mass of the man is 80. And the acceleration of the man in the lift is 1 meter per second. So 1. And that's equal to Fn. So Fn is going to equal 704 newtons. In other words, he's going to feel lighter because he's accelerating downward. Let's move on to question 5.2. The diagram below shows two blocks, A and B, of mass 20 kilograms and 10 kilograms respectively, connected by a light inextensible string over a frictionless pulley. Block A is held at rest on a rough surface. So we've got this diagram, and 5.2.1 define normal force. We'll come back to it. When block A is released, it accelerates to the right. So acceleration is this way. The tension in the string is T, and the coefficient of kinetic friction between block A and the surface is 0,25. So mu K is equal to 0,25. Question 5.2.2, draw a labeled free body diagram showing all the forces acting on block A while it accelerates. Now this is worth 4 marks, meaning that we need to show 4 forces. Now when you're drawing your free body diagrams, please ensure that you draw it in pen, because you aren't allowed to draw it in pencil. If you do, it will not be marked. Also, if there are components, do not draw in the components, because that also will not be marked. Really, you will be penalized. So the forces acting on this are going to be the normal force and the force of gravity. Now the normal force and the force of gravity are equal to one another, but in the opposite direction. So also take note that the length of the arrow should also be more or less proportional. Then there's tension. Tension is going to pull it to the right, so Ft. And there's going to be friction, so Fk. It's moving, so there's going to be Fk. Now, I've drawn Ft larger than Fk because the object is accelerating to the right. So there's my 4 forces, 4 marks. Question 5.2.3. Calculate the magnitude of the acceleration of the blocks by applying Newton's second law separately to each block. Now for block B, the forces that are acting on it are going to be the force of gravity and tension. Now the tension force that's acting on A is going to be the same as the tension force acting on B. So that's going to be our link. That's what we're going to use to join the two to get to work out the acceleration. So for block A, I'm going to say F net equals ma. Now it's accelerating to the right, so I'm going to choose the right as positive. So ft minus fk is equal to ma. Now I can substitute. I don't know what tension is, so let's leave that as ft minus fk is mu k times fn. Now mu k was given to us as 0,25, and the normal force is equal to the force of gravity since the object is not moving up or down. So force of gravity is going to be the mass, which is 20, times gravity 9,8. And that's going to equal ma. So the mass of the object is 20 and the acceleration a. Now it's clear we have two unknowns, and so we are going to need to do simultaneous. Now b is going to move downwards, so I'm going to keep down positive. I'm going to say F net equal ma. That means Fg minus Ft is equal ma. Now for B, the force of gravity is going to be 10 multiplied by 9,8 minus Ft is equal to ma. Now it would be very useful here to rearrange these equations such that I have T the subject of the formula, because then I can equate T and then solve. So I'm going to say here that Ft is equal 20a plus 0,25 times 20 times 9,8. You can of course simplify that. I don't have a calculator on me, so I'm not going to do that. Then for B, I'm going to say that 10 multiplied by 9,8 minus ma, so mass is 10, acceleration is a, and that's going to equal Ft. Now that's going to be my equation 2, and this is going to be my equation 1. So Ft is equal to Ft. Then I'm going to say 20a plus 0,25 multiplied by 20 multiplied by 9,8 is equal to 10 times 9,8 minus 10a. Now we can simplify. We'll get 30a is equal to 49. That means a is equal to 1,63 meters per second. So m dot s to the power minus 2. The question asked us to calculate the magnitude of the acceleration, so we don't need to put a direction. Let's move on. A 4 kilogram block is now placed on top of block A whilst it is accelerating to the right. The 4 kilogram block does not slide. So how will the tension in the string be affected? Choose from increase, decrease, remain the same. Explain the answer. So to solve this question, what we'll do is we'll look at the system as a whole. So F net equals ma. Now, since the mass of A is increasing, there's something that's going to be on here. The mass of the entire system is going to increase. So the mass increases. Now, if the mass increases, that's going to have an effect on both the net force and the acceleration. Because as we know from Newton's second law, that the net force or the resultant force is directly proportional to the acceleration, or rather the acceleration is directly proportional to the net force and inversely proportional to the mass. So meaning if the mass increases, not only will the acceleration decrease, but also the F net will decrease. Now we're going to use that and we're going to figure out what's going to happen to the tension. So I'm going to use object B to figure out what's going to happen to tension, because remember A and B are still joined by the same rope. So whatever I do to B in terms of figuring out the tension, the same will apply to A. And the reason why I'm doing it is because A has now become more complex. because now there's a block on it and the free body diagram will be slightly different and so on. Whereas with B, nothing's really changed and the tension is still going to be the same as the tension in A. Now, for B, remember we said that F net equal MA. B is still going to move downwards, so I'm keeping down as positive. I'm going to say that FG minus FT is equal to MA. Now I'm going to rewrite this. So FT is going to equal mg, so the mass of gravity, or the mass times gravity, minus ma. Now the mass of B hasn't changed. So this mass and this mass is the same. So I can take it out as a factor. So Ft is equal to, let's take it out, so it's 10 into 9,8 minus whatever the new acceleration is. Now, let's look at what happens to the acceleration and then we can figure out what's going to happen to tension. So we said that the acceleration is going to decrease from here. So whatever the acceleration was, if the acceleration decreases, it means that this bracket is going to get larger, the whole bracket. Right? We can see that if we take an example, say 9,8 minus was 1,63. So 1,63, we'll get some value. But if we decrease that acceleration, we say 9,8 minus, let's make it 1. That's going to equal 8,8, 8,17. So it's clear here that the difference has increased. So if this increases, it means that Ft will also increase. Let's take a look at question number 6. The mass of planet Jupiter is 300 times the mass of Earth, and its radius is 11 times larger than that of Earth. An astronaut has a mass of 120 kilograms. Question 6.1, we'll leave it out. Question 6.2, what will the weight of the astronaut be on the surface of Jupiter? So what I'm going to do is I'm going to calculate the acceleration due to gravity in relation to, compared to Earth and Jupiter. So 6.2, we know that the gravity on Earth is equal to gme over r squared. So then the gravity on Jupiter will equal g multiplied by the mass of Jupiter divided by the radius of Jupiter all squared. We also know, so J, that the mass of Jupiter is 300 times the mass of Earth. So 300 me divided by the radius of Jupiter is 11 times that of Earth. So 11 re all squared. Now let's simplify a bit. So this is going to give us 300 gme divided by 11 squared, which is 121. So 121 re squared. Now let's simplify a little bit. 300 divided by 121 is 2.479. So 2.479, and this is going to be GE, because this here is the same as this. And we know the gravity on Earth is 9,8, so 2,479 multiplied by 9,8, and that is equal to 2975 meters per second squared. Now that we know the acceleration due to gravity, we can calculate the weight. So the weight is going to equal 120 multiplied by 24,2975, and that's equal to 2915,70 newtons. So question 7 says two spheres P and Q placed on insulated stands carry charges of 5 microcoulombs and -8 microcoulombs respectively. Question 7.1.1, explain why the charges are on insulated stands. So they are on insulated stands, so there's no conduction of the charges. So they are on insulated stands because there must be no conduction of charges. We want the charges to stay on the sphere, so no conduction of charges away from the spheres. It needs to stay on them. Now 7.1.2, the charges are brought into contact and then separated. Are electrons transferred from P to Q or from Q to P? Give a reason. Electrons are going to be transferred from Q to P, and that's because electrons move from the more negative, so more negative to less negative, or you can say more positive body. So P has a positive charge, Q has a negative charge, Q is more negative, and so the electrons are going to go from Q to P. Question 7.1.3, calculate the number of electrons transferred. This is worth 5 marks. So first we need to calculate the charges after contact. So Q new is going to equal Q1 plus Q2 divided by 2. Now both of them are microcoulombs, so we can say -8 plus 5 and then times 10 to the -6 all over 2. And that's going to give us -1,5 times 10 to the -6 coulombs. Then if you want to calculate the number of electrons transferred, so electrons transferred, we can use the formula N is equal to Q final minus Q initial divided by QE. So now we can, it's really our choice, whichever sphere we want to use, because we'll either get a positive or negative value. So let's use P, since P has P is gaining electrons. So the final charge for P is going to be -1,5 times 10 to the -6 minus the initial charge of P is 5 times 10 to the -6 divided by the charge of an electron here is going to be -1.6 times 10 to the -19. And that's going to give us 4,063 times 10 to the power 13 electrons transferred. Question 7.1.4, name and state the law. So this is the law of conservation of charge, which states that the total charge in an isolated system remains constant. Okay, moving on, let's look at 7.2. R is a point of magnitude 6 nanocoulombs. So R is there. 7.2.1, draw the electric field pattern. So since it's a positive charge or a point charge, the field is going to go outward. So we will have a positive sphere like this, and we will have our field lines like so, with arrows pointing away. Remember, the arrows should not touch, nor should they cross. Question 7.2.2. So S is a point charge of magnitude -9 nanocoulombs placed 25 millimeters to the right of R. Z is a point X millimeters east of point charge S. Point charge R and S and point Z lie on the same line. 7.2.2, state Coulomb's law. That's a long definition. Let's leave it out. 7.2.3, calculate the magnitude of the electrostatic force that R exerts on S. Okay, so R on S. So we can calculate using F is equal to K, Q1, Q2 divided by R squared. Now K is 9 times 10 to the power 9. Q1, well, here we're going to use R, so that's 6 times 10 to the -9. S is 9 times 10 to the negative 9. Remember, when you are using this formula, we do not substitute in the sign. Divided by the distance between them. Remember, the distance need to be in meters, so we need to convert that. 25 millimeters divided by 1,000, that's going to be 0,025 meters, and we are squaring this. And that's going to give us a force of 7,78 times 10 to the negative 4 newtons. They ask for magnitude, so we don't need to give any direction. Question 7.2.4. The net electric field at point Z is 7,66 times 10 to the 5 Newton coulombs west. Calculate the value of X in meters. Okay, so in order to calculate this, we are going to calculate the electric field for S on Z and then R on Z. And then the net is going to be, well, either the sum or the difference of that. So I'm going to draw in a free body diagram showing the electric field that's acting on Z. So if this is Z, and remember, when we talk about point charges or points, it's simple, just imagine it as a positive charge. So if Z is a positive charge, then S is going to want to pull it to the left. So there's going to be an electric field this way. So this is going to be the electric field of S on Z. Then let's look at R on Z. R is positive, Z is positive, so R is going to want to push Z to the right. So this is going to be here. So this is going to be the electric field of R on Z. Now, since they tell us that the net electric field is to the west, let's choose west as positive. So west is this way, and I'm going to choose west as positive. So that means that E net is going to equal the electric field of S on Z minus the electric field of R on Z. Now that we have an equation, we can then substitute and solve. So we know the net electric field is 7,66 times 10 to the power 5, and that's equal to the electric field of S on Z is going to be K. Then let's substitute, we know what K is. So 9 times 10 to the 9. Then the charge of S is minus 9 nanocoulombs. We're just going to put 9. So 9 times 10 to the minus 9 divided by the distance between S and Z is X millimeters. So we're going to convert that. So that's going to be X over 1,000 all squared, because we want that in meters. And then minus the electric field of R on Z. So R is, so 9 times 10 to the 9. Then the charge of R is 6 times 10 to the minus 9 divided by, and R is 25 plus X meters away, or millimeters away. So we're going to add here 25 plus X divided by 1,000 all squared. And now it's just a matter of solving. So we're going to use our calculator here. We're going to use shift solve on our calculator. We'll get that X is equal to 0,01 meters. Let's move on now to question number 8. A bar magnet moves horizontally toward a solenoid. So we've got that, we've got a solenoid, and they ask us, question 8.1, state Faraday's law of electromagnetic induction. We leave that out, but basic idea is the magnitude of the EMF across the end of a conductor is proportional. So you have access to it, so just please go through it. The graph below shows the change in magnetic flux versus the change in time as the bar magnet moves through the solenoid. Question 8.2, use the graph to calculate the rate of change of magnetic flux linked to the coil. So 8.2, so they want to know the rate of change of magnetic flux. So the rate of change of magnetic flux, rate of change of magnetic flux. So what is that? So rate of change means we are dividing it by time, and then change of magnetic flux, so delta phi. So what we're looking for is delta phi divided by delta t. And since we have delta phi on our y-axis and we have delta t on our x-axis, what we're essentially looking for is the gradient. So we pick 2 points here, and doesn't really matter what points we pick. I'm going to go with the simplest ones. I'm going to go with 6 and 0. So gradient is going to equal 6 minus 0 divided by 4 minus 0, and that's equal to 1 comma 5. Now rate of change of magnetic flux, so magnetic flux is measured in WB or Weber, and then over time, so seconds to the power minus 1. Question 8.3, calculate the magnitude of the EMF induced across the coil if the coil has 120 turns. So here we're going to use the formula. EMF is equal to minus N delta phi divided by delta T. Now, we know delta phi divided by delta T is the gradient. And we've already worked out the gradient as 1,5. So this is going to be minus 120 times 1,5, and that's equal to minus 180 volts. You could put 180 volts if you wanted, but you can also leave it as minus 180. Question 8.4. This is a theory question. State 2 ways by which the induced EMF in the coil can be increased. So you increase the speed at which the magnet moves through the coil. You can also increase the number of turns, so increase N or number of turns. And you could also increase the strength of the magnet. Increase magnet strength. Okay, now let's move on to question number 9, electric circuits. The circuit diagram below shows 3 identical light bulbs, X, Y, and Z, connected to a battery of negligible internal resistance. 2 voltmeters, a switch, and 2 ammeters are also connected in the circuit as shown below. So we've got the circuit, switch S is opened. Okay, how does the brightness of bulb X compare to that of bulb Y? Choose from X is brighter, X is dimmer, or X and Y are equally bright, and give a reason for your answer. Okay, so let's follow the path that current is going to take here. So this is my bulb. There's my battery, there's the bulb. We're going to go this way. There's going to be no current flowing through this branch because this switch is open. So we're just going to have this. So essentially that's my circuit. And so the answer then is going to be that X and Y are equally bright. And so we can use the formula P is equal to I squared R. Both of them have the same current going through it because it's essentially a series circuit. So same current through X and Y, and they are identical, so same resistance, same R for X and Y. And so since the current is the same and the resistance is the same, it means that they're going to have the same power and same brightness. So same power and brightness. Moving on, they tell us now that the switch is closed. So we need to make a change to our circuit. So 9.1.2. Which of the ammeters, A1 or A2, will have a higher reading? So A1 will have a higher reading, and that's because it's reading the total current. A2 is in a branch, and so it's reading only a part of the current. Question 9.1.3, using relevant equations, show that the reading on V1 equals 2V2. Okay, so all we need to do here is let's allocate values. So if this resistance is X, right, this resistance will also be X, and this resistance will also be X. But these two are connected in parallel. So the effective resistance of the parallel branch is going to be Rp equals R1, R2 divided by R1 plus R2. So this is going to be X times X divided by X plus X. So that's going to give me X squared divided by 2X. We can cancel an X and an X here. That simplifies to half X. So the effective resistance of the parallel branch is going to be half X. Then we can calculate the voltage. So V, we can calculate V1 here. That's going to equal I times R. So the current that's going through X is going to be the total current. So that's going to give me X multiplied by I, whatever the current is. And that's going to be V1. Then, if you want to figure out the voltage on V2, because they are in parallel, V2 is going to equal the voltmeter here, which is going to be the voltmeter for the entire parallel branch, because remember, voltage stays the same in parallel. So V2 is going to equal I multiplied by R. Now the resistance we calculated was half X. So V2 is going to equal I times half X. So if we bring this to the front, we're going to get half multiplied by I times X, which is equal to half, and I times X is V1. So half of V1. So V2 is equal half of V1. Actually, they wanted it the other way, so we can say if multiply by 2, then we'll have 2V2 is equal to V1. The same thing. Okay, moving on. Bulb Y burns out while switch S is closed. So Y burns out. So that means that's gone. So now we essentially have this as our circuit. What effect will this have on the reading on voltmeter V2? Choose from increase, decrease, or remain the same. Explain your answer. So let's take a look at what effect this is going to have on our circuit. By removing a resistor in parallel, so R in parallel was removed, that's going to have an effect on our total resistance. The total resistance in the circuit is going to increase. And because of this, the total current is going to decrease. Remember that I is equal to V over R. They are inversely proportional. So what does that mean for V1 and V2? Remember, the V total is going to be the same, right? The voltage from the battery is the same. And so then the V total is going to equal whatever V1 is plus whatever V2 is. Now, V1 is going to be affected as well. Now, V1 is going to have a lower value. And the reason for that is because, remember, V is calculated by I times R. Now, if this is constant, right? So the total current, as we said now, is going to decrease. So this is decreasing. And the resistance for X is staying the same. So that means V1 must decrease. And if V1 decreases, V2 has to increase in order to keep the V total constant. So the answer then is V2 will increase. Okay, let's move on. Question 9.2. An electric iron has specifications 220 volts, 2000 watts. Calculate the cost of using the iron for 15 minutes if the cost of electricity is 2 2 Rand 80 per kilowatt hour. So the cost is going to equal the power usage multiplied by the time multiplied by the rate. So how much they are charging. Now the power was given as 2000 watts. Now 2000 watts needs to be converted to kilowatts. So 2000 divided by 1000 multiplied by. Now the time needs to be in hours. So 15 minutes converted to hours is 15 over 60. Multiplied by the rate is 2 Rand 80. And that's going to give us an answer of 1 Rand 40. So it's going to cost you 1 Rand 40 to use the iron for 15 minutes. Moving on now to question number 10. 3 resistors are connected in an electric circuit as shown in the diagram below. The ammeter and the connecting wires have negligible resistance. The voltmeters have a very high resistance. The battery has an EMF of 12 volts and significant internal resistance. Okay. Question 10.1. So they tell us the voltmeters V1 and V2 read 8 volts. So this is 8 volts and 11.8 volts respectively. So 11.8 V. Question 10.1. Calculate the reading on the ammeter. So 10.1. To calculate the reading on the ammeter, we can simply say that I is equal to V divided by R. The voltage for the 10 ohm resistor is 8 divided by the resistance of the 10 ohm resistor is 10. So 8 divided by 10 is 0, 0.8 amperes. So this is 0, 0.8 amperes. Question 10.2. Calculate the resistance of resistor R, and that's worth 5 marks. So resistor R is connected in parallel to resistor or the 20 ohm resistor. So what we can do is we can calculate the effective resistance of that parallel branch. So R parallel is going to equal, so R1 R2 divided by R1 plus R2. This is going to be 20x, so or rather we say 20 times R divided by 20 plus R. Now we can't simplify that further, so we leave it like this. Now what we can do is we can work out the voltage that the parallel branch is going to be using. So if we know that both, so this and this is using up 11.8, we can subtract 8 from the 11.8 to work out what the parallel branch is going to be. So the voltage for the parallel branch is going to equal 11.8 minus 8. And that's going to equal 11.8 minus 8, and that's equal to 3.8. So 3.8 volts. Then we also know the current going through the parallel branch. So the current through the parallel branch is going to be 0.8 amperes. And so we can use Ohm's law formula to calculate R. So we can simply say that RP is equal to VP divided by IP. So the voltage in parallel is 3.8. The current in parallel is 0.8. And that's equal to RP, which is 20R divided by 20 plus R. And now you can use your calculator's function, shift solve, and you can then solve for R. So R is going to equal 6.23 ohms. Let's look at 10.3. Calculate the internal resistance of the battery. So we can use the formula EMF is equal to I into big R plus small r. So the EMF is 12. Total current is 0.8. Total resistance can be calculated. So the total resistance is going to be whatever is in series plus the resistance in parallel. So the resistance in series is 10 and the resistance in parallel, so 4.75. So our total is 14.75. So 14.75 plus R. That means R is going to equal 0.25 ohms. And that's the whole paper. Guys, if you stuck around till the end, please do leave a like, share, and subscribe. It really does help. And I'll see you in the next one. Bye-bye.